So hello everyone. Today we'll talk about data compression. We'll talk what is the data compression and the ways how we can compress the data. So let's start.
So data compression, as you may assume from the name, it just compresses the data. Why do we need to compress data? Because it allows us to save the space in the memory, and when we have like smaller data, or if it takes less space, it's easier to transmit that data. And if it is easier and lighter to transmit, it means that we can save the time to transmit it. And the data compression is necessary because like in a lot of the files, a lot of the documents, they have a lot of the redundancies that can be compressed or it can be cut. So the data compression is widely used in our modern world. Um, like we have a lot of file compressions, and usually most like a lot of you may use is gzip, bzip, or 7zip, or it can be file systems like ntfs, hfsc, and zfs. These file systems can be used in your laptops, and it can compress any kind of file without like specifying the what kind of files. And some we have some kind of data compressions that specify the exact um, type of the files. For example, if we want to compress the images, usually it used the GIF or JPEG uh, extensions. This JPEG or GIF actually it's a data compression um, application. In order to compress the data, the music, we can use the MP3. In order to compress the video, we can use MPG and HDTV. And also the data compression is used also in a communication, like in a transferring data between the applications, the between two endpoints of the application. For example, Skype. In Skype or Zoom. In a Zoom or Skype, we have two endpoints where we need to transmit the data from one point to another. And in order to increase the speed of the transferring the data, we can use the data compression. Also, in transferring the data in a fax, it can be used this kind of protocol. All the data compression is very similar in terms of the basic model. Like in today's world, everything, all the data can be represented in a binary. Like all the data can be used with the bits or bytes. And this data can be represented as a byte stream or bit stream. So all the data compressions have this kind of like sequence of the work. So let's say that we have some kind of original bit stream B, we have some original data, and we have a box that compresses this data. So after the compression, we have some compressed version, and let's say that we need to transmit this data from one point to another, and we can use the box that expands this data. And this box allows to convert the compressed version of the data to our original bit stream. And also, usually we need to measure the efficiency of our data compression algorithm. And the efficiency can be measured in a compression ratio, like how many bits it takes in compressed, proportional to the original number of bits in our data. So as I said before, there are many kind of algorithms to compress data, but there are two algorithms that are most one of the main or one of the first data compression algorithms. The first one is the Harmonic coding, and second one is the LZW compression. Actually, in a previous course of Introduction to Algorithms, we have already covered the Harmonic coding, but I want to go one more time again um, and talk about and remind ourselves what is the Harmonic coding. Then we will talk about LZW compression. So let's start with the Harmonic coding. Harmonic coding is an algorithm for compression of the data. It was developed by David Hoffman while he was a student at MIT, and the algorithm was published in a paper of method for the construction of minimum redundancy code in 1952. So in Harmonic coding, what do? We just first go through the text or from the document, and we count how many times each character repeats. Like uh, after the going through the document, we take the statistical data, and here as you can see, let's say that character A repeats 10 times, um, character E repeats 15 times, I repeats 12, and here is the other information about each of the characters. So what do we do first? We sort these characters according to the frequencies, and we have this kind of sorted data. And then we just start to build the tree from these nodes. And we take first, on each step, we take the frequencies with the least number. So as you can see, the characters with the least number are the T and O. So we just merge these two nodes into one tree, and the root of this tree is 4, which is actually just the sum of the frequencies of the T and sum of the frequencies of the O. So then we have this kind of list. Then we merge these two nodes, and here we have in the root we have 8 because it's sum of all the frequencies of this tree. Here we have the 8. Then we merge the next two least number of frequencies, this node and this node, and we get the new tree with the root of the 18. So here, as you can see. Then on next step, we see that the least number of frequencies are this node of 12 and 13. So we merge these two trees, and we have like 25. One tree with a root of 25 and one tree with a root of 18. So here, as you can see, we have 3 options to merge, and the least number of nodes are this one, 15 and 18, and this tree with a node of 18. So we merge them, and we have, when we merge them, we have 33, and we have here in the end only 2 separate trees. We merge these separate trees in order to get one big tree, and we got in the end this kind of big Huffman tree. So what do we do next? We go from the root, and for subtree, for each pass to the right we give value of 1, for each pass to the left we give 0. So and we repeat it until the end of our tree. And in the end, each character, they get the value that is in a path to that character starting from the root. For example, let's take T. In order to get T from the root, we first meet 1, then we again meet 1, then we turn to the left and we get 0, then again 0, then again 0, and then we reach our node with a T. Or maybe, for example, let's take character A. In order to reach A, first we start from the root, it's a 1. Then we again go to the right. Then again go to the right. Meanwhile, let's take for I. To reach I, we go to the left. So it's for 0. Then we go again to the 0. So as you can see, the characters that are repeated less, they get the longer value. And the characters that repeat a lot, for example I, they got very small value. So the characters that are repeated a lot, they get the less value that allows to save or compress the data. So in the end, we have this kind of results. Each character has its own value, and this is the result of our data compression. Next algorithm is called LZW. So LZW is kind of big improvement to the Huffman compression. It was implemented by Lempel, Ziv, and Welch in the late 70s and early 80s. The big difference between Huffman compression and LZW compression is that in this LZW compression, we don't need to go at least once before we need to compress. We can compress the data as we go through the text. So what is the LZW compression? We learn how to compress our data, what is the model of our compression progressively. And this allows us to produce a more accurate modeling. And when we decode the text, we need to always start from the beginning. So in order to use LZW, first we need to use ASCII code with a hexadecimal format, because like in a hexadecimal format, it makes our coding more using the less digits, and for the clarity and for the economy, we use the ASCII code of the hexadecimal, and we use 80 to say that this is the end of our file. And for the additional coding, we use the values between 81 until the FF. So first we have this kind of input, and we have this kind of ASCII code. These values, they are in the hexadecimal format. So initially we have the values for each separate character, the value from the ASCII code. So what do you do? Again, I want to remind that this compression works in on the way to compress the data. What do we do? First, we say that we first meet A, and we say that the value is 41. Then we have the then we have the B, and B's value is 42. But these two prefix we have never met, and that's why we say that AB is equal to the 81. Kind reminder that 80 means that this is the end of the file, and everything after the 80 is additional k in our compression. Then here we have never met this prefix before, br, and we say that this br has a value of 82. So we add up this k and the value into our table. Then we have r, and r in our ASCII code is 52, and we say that this prefix ra has value of 83. Then we have A. Um, A has a value of the 41, and we see that AC has value of 84. Then we have C, and has value of 43, and we see that CA has value of 85. Then we have the A again, so it's a value, it has value 41, and we add AD, the prefix that we had never made before. We add that prefix into our table, and AD has value 86. Then we have D. D has 44, and we say the DA is in our table, so DA has a value of 87. Then, as you can see, we have A, and the next letter is AB, but we have this prefix AB, and instead of putting the value for each character separately, like for the A separately and for the B separately, we just put one value for both of these characters, and we say that it's 81. Then we have the R, uh, and if we check the next letter after the R, we see that it's A. R. Actually, we have already covered this prefix RA, and it has a value of 83. Then BR, it has a value of 82. Then the next moment is, as you can see, we have first checked the next letter, and we see that uh, we have A, then we have AB. AB actually it's in our prefix. Then we check one more letter, and we see that ABR it's also in our prefix. Then we check A, but ABRA is not in our table. That's why we only put ABR and gives a value of 88. And the last one is A, which is just last letter, and we say that it's a 41. And in the end, we need to put 80, means that this is the end of our file. So this is our compressed data of our input of our original data. Um, so LZW LZW can be represented as a try, like these values can be represented as a try to make our lookup much faster. Like, for example, if first means A and the next letter is B, we can easily check if the next letter is R or not. If it is R, then we go to the next character.